This example problem deals with radiation dose. I'll begin by describing a radioactive source, maybe a gamma emitter, that has an output power P, that would be measured in watts, joules per second. A person is near this radiation source, and her effective area over which the radiation can be incident on, this symbolizes A, measured in square meters. The P here is a power. It's P subscript A. It represents the absorbed power, the power absorbed by that person, measured again in joules per second. The power absorbed is a certain ratio or fraction of the broadcast power from the source P, and that ratio or fraction is the ratio of the areas. The area effectively of the person divided by the area of an imagined sphere whose radius is r, where r is a distance from the radioactive source and the person, measured in meters. Let's work a sample problem involving a calculation of radiation dose. In this example, the area of our person is 1.90 square meters. That person is 2 meters away from the source. The output power of the source is 0.08 of a watt. 0.8 of a watt, I meant to say. 0.080 watts. We first will calculate the absorbed power. It'll be some fraction of the broadcast power, some fraction of that, measured in joules per second or watts. Here is that calculation repeated from this equation. It's the ratio of the area of the person, 1.9, to the area of this imagined sphere on which she's imagined to be standing. And then we multiply times the source power, which is 0.80 watts. We get that number there, 0.0302 watts. Now imagine this person is working steadily at that location for 6 hours, which works out to 6 times 3,600 seconds, or that many seconds. All right, now let's take a step further and discover what was the energy absorbed during that 6-hour time period. Well, incident on her body is that fraction of a joule each second. We'll multiply it times the number of seconds to get the total number of joules absorbed by that person. 652.32. Now, for the first time in this class or the previous one, I'll introduce a non-standard unit of energy that's convenient for our purposes. It's the centijoule, analogous to a centimeter, which is 100th of a meter. A centijoule is 100th of a joule, abbreviated lowercase c, upper j. Here we go. Multiply this by 100 and move the decimal point over twice, and you have 65,232 centijoules. And I'm recording for historical purposes that a joule is 100 centijoules. Something else you need to know. There is a unit called the rad, which will turn out to be the unit of dose. A rad is that. It's 1 centijoule per kilogram. So for example, if a person absorbed full body exposure 100 rads, then she would have absorbed 100 centijoules for each one of her kilograms, or 100 joules for every one of her kilograms. Now we define the quantity that we've been talking about, dose. The dose that a person receives is the ratio of the energy received in centijoules to the number of kilograms of that person's mass, E over m. So let's assume that the person we're talking about that's standing 2 meters away from a source, this source, is 80 kilograms. So we divide the number of centijoules by the mass in kilograms and get 815 CJ per kilogram, centijoules per kilogram. But recall, a centijoule per kilogram is a rad. Final result, this person unfortunately received a dose over that 6-hour period, 815.40 rad. What does that mean? Well, if you were to absorb 1100 dose, your chances are 90% of dying within 30 days, even with intensive medical care. But with less than that, 815 centijoules per kilogram, 815 rads, 90% of the people will die within 60 days. Back up, I've got that backwards. Only 50% of these poor folks will die within 60 days, even assuming intensive medical care. It's not as bad as a 90% chance of dying if you have more than 1100 rads. Well, on that worrying note, I'll end this discussion. I hope you get something out of it. In the notes, I do not introduce the unit centijoule, but you don't have to see everything I think is important in the notes. Some of it is found on your video lectures, and this is one of them. I hope you are enjoying all of the videos. If not, maybe you're finding something better to look at.